Thank you. Good morning. My name is Joe Fish-Kay. I'm Principal Research Scientist in Emerging Technologies, and today I have the pleasure and joy of introducing Andrew Head, who's a graduate student at UC Berkeley in Bjorn Hartmann's group. I met Andrew at a conference called Chi, and Andrew and Bjorn told me a little bit about the work he was doing. And what I thought was fascinating was how vital and how important this work is for the stuff we do at Mozilla every day, both in the terms of the work that we do at MDN, in which we're explaining the web to the world, but also the work that we do internally in which we collaborate on code, we document code, we collaborate with people at great distances, at great times. And I thought he'd be a great person to come in and talk about some of that stuff. So, without any further ado, Andrew.
Thanks, Joe Fish, for that kind introduction. I'm really excited to be here today as part of this Emerging Technologies seminar series. I really love Mozilla and a lot of the ideals of openness that drives a lot of the work. And I think those same ideals motivate a lot of this work that I'll be presenting today called Bionic Tools for Documenting Code. So the Bionic Tools for Documenting Code was designed to overcome a lot of problems that I see in my day-to-day work as a programmer. Problems like, in documentation, having bad usage examples. Here's an old Nabble post that has a code example right in the middle of it. And this is a bad usage example because in order to actually use it, it requires another 30 or 40 lines of boilerplate code in order to get it to run. It requires a meaningful piece of data. And if I just want to use this 5-line code snippet right here, it's going to take a lot more effort than just finding and reading this code example in order to get it up and running. Other issues like missing explanations for code. Here's a command called openSSL, and you can use this in order to generate certificates for an HTTPS server. But in order to use this and modify it and understand it, a lot of questions will come to someone's mind. For instance, what is this RSA :4096? Is it important that this 4096 is a power of 2? Is there some other way for me to change the encryption for this? How about this X509? If I get rid of this, will it make my server less secure? A lot of times, the accompanying explanations for code examples like this just aren't there, which makes it really difficult for people to understand, work with, and modify this code for their own purposes. Documentation in general lacks the attention that it deserves. We as programmers have a lot of things that demand our attention, fixing bugs, developing new features, and documentation often hits the cutting room floor. And this is a problem because writing documentation is something that's fundamentally iterative, time-consuming, creative. It requires us to think about what we want to document and what our audience knows, and to be able to put that in words and try things out and put it in front of people and make sure that we're communicating ourselves properly. That said, it's really hard to justify the time that it takes to write documentation. In the words of one of our maintainers in one of the studies that I'll be presenting in a bit, they told us about one of their files of documentation that it's unlikely that this will ever get changed again. And if I hadn't scheduled this meeting with them, they would have forgotten the file existed. This isn't out of the ordinary. We have so many projects that we're working on that oftentimes helping people on the projects that are already there is something that gets neglected. My work at Berkeley is all about what I call bionic documentation tools. These tools that are aimed to help programmers capture, share, amplify, shape their insights, and share them with other programmers. I focus on two of the really key parts of documentation, producing usage examples and explanations. And it's bionic because it combines both automation and human insight. The human insight part is very important. It's what brings the goals to documentation. What should I document? Domain knowledge. What do people need to know about, and how should I explain this in a way that's task relevant to them? And then this idea of empathy. Who's my audience? What details do I have to share with them so they're capable of getting up and running with this code? This human part is really important to producing documentation, and it's something that we're not going to get rid of anytime soon. The other part of bionic documentation is the automated side of it. The side that's capable of guaranteeing the correctness and completeness of code examples, as capable of giving existing documentation and ideas greater reach than they would have if a programmer was to just write a single documentation page, and to be able to adapt this documentation to new audiences and new pieces of code using the same fundamental insights. All this together, the human side together with this automated side they come together into these Bionic documentation tools, which leverage code analyses in many different ways to help programmers capture, shape, amplify, and share their insights with other programmers. In this talk, I'm going to talk about 3 different projects that I've worked on during my PhD research that are aimed to help programmers share examples and explanations of code with each other. The first of these is called CodeScoop. And it's an intelligent assistant that plugs into your editor that helps programmers extract examples that are tailored to a specific audience out of their own tangled code. The second project is called Tutorons. It's called Tutorons because you can imagine it as atoms of tutorials, these context-relevant explanations that can be added on the fly to existing code examples in tutorials. And then the last one is a project about telemetry. How can we learn more about the questions that API users have about the APIs that they're using? How can we get these questions in a way that's ecologically valid, in a way that captures these ephemeral questions that might only come up once every few hours during part of programming work? So I'm going to lead in with the CodeScoop project, which is all about providing an intelligent assistant to help programmers extract usage examples out of meaningful patterns in their own code. Why did we focus on code examples? Well, code examples are a really great currency of knowledge exchange for programmers. We use them all the time in our tutorials, in our online textbooks. We use them in online Q&A, things like Stack Overflow, in order to communicate these insights about how to do things in just a few lines of code. We share them over chat in order to explain to other people what we've done and how they can build on it. And we also post them on code sharing sites for other people to build on and extend. Mark Sachs has a great quote about code examples and their role in on-the-job learning. In 1994, when he observed programmers working, he said that people learn more and do more work by copying and following examples and by working their way through exercises than by any other single activity. Code examples are a fundamental part of the craft of learning how to do new things on the fly and picking up new technologies. The main question that was behind the CodeScoop work was, how can tools make it easier for programmers to share examples that are based on their own code? So when a programmer has a program that they've written, which might be detailed, highly personal, highly tangled, have a bunch of business logic in it, how can we help them extract out a concise, pithy, self-contained, executable code example that demonstrates an important pattern, which then they can do with whatever they want. Serve any of the purposes that we usually do with usage examples, sharing it as know-how over chat, posting it to blogs, wikis, Q&A, and so on. And the reason we wanted to build a tool for this is because simplifying code and making it executable and tweakable by other people is actually a really challenging thing. Once you try to make these examples usable to other people, rather than just copying and pasting chunks of code, it becomes a very involved process. When we invited programmers into the lab to make executable examples from interesting patterns in their existing code, it was this tedious and time-consuming process. So this is an example of a work environment of one of these programmers who is trying to create an executable example. And you can see there's a lot going on. Here's an editor where they were building up this example slowly by moving lines of code over from their original source program. This programmer also had yet a third editor open as a testing environment where they could run this example and make sure that they hadn't broken anything about the behavior they wanted to preserve. And then they also had a browser open so that they could recall some of these details about their code that they might have forgotten since they originally wrote it. There were tons of errors that were introduced through the process of producing examples. For instance, transcription errors, and errors introduced when they edited the code in order to tweak its behavior. Sometimes they forgot code. You can imagine that sometimes your copy and paste is going to be incomplete and you find out they're undefined variables, undefined imports. And if a programmer started with a big project and tried to whittle it down into a pithy example, this could be really time-consuming too, requiring them to identify a lot of dead code. And so while none of these errors is particularly nefarious, and while most of these things were relatively easy to fix, they happened all the time, making something that would otherwise, that should take only a few minutes, take a long, long time in order to iteratively go through trial and error, pulling code out and fixing it up in the pursuit of trying to produce usable examples. From this study, we decided that an intelligent assistant for creating code examples should do a few things. It should be able to suggest lines of code that the current example needs to run that you're building up. It should constrain your manual code edits to make sure that you can make these changes, but that it will continue to preserve the behavior and compile. It should enable early and frequent testing of the code so that if you do make any edits, you can check them right away to make sure that they haven't broken anything important. And in order to keep these code examples concise and easy and ready to plug in, it should omit code except for explicit selections that a programmer has made and fixes that they've made to those examples. Our vision of a tool was, say this is a code example that fetches a line from a database that I want to share. And it ends up storing this in some important data structure like this book data structure that I want to use later. The vision of this was, say that that piece of code is this tasty ice cream. We wanted to make a tool that made it possible to scoop out the relevant parts of the code and serve it up as a tasty example for other programmers to consume, play with, and read. And we called it Code Scoop because we were designing this scooping interaction for code examples. Oh, at this point I want to show you a little bit about what Code Scoop looks like to use and how we embodied some of these ideas of what an intelligent assistant for making usage examples would look like. So I'm going to pull up a demo. Okay. Cool. So here is a piece of existing code that a developer has written. It's got a bunch of logic in it that ultimately what it does is it queries a database for a row out of that database, and then it stores it in this book data structure that we've been talking about. Let's say I want to scoop out a relevant usage example for someone else to use. My first step is to identify kind of the core of the pattern, the part of it that should absolutely be there that represents an interesting pattern for someone else to reuse. Here it's really embodied in this line right here, which uses this cursor data structure in order to get the data in a particular column of a row. I start out by clicking this scoop button here. And the first thing that happens is that the editor breaks into two panes. On the left side, we have the original source program. And on the right side, we have this work in progress code example that I'm going to be building up. The first thing that CodeScoop does is it wraps this in some boilerplate that will allow it to compile and run. But it also starts flagging some of the errors of some of the things that I've missed in this example. For instance, this undefined cursor and column index title variable. It then assists me in resolving this usage example and building out into something complete and executable. So for this cursor variable, I can click on this define button, and it provides me with what's essentially a quick fix, except it's grounded in the original code. So it points me to the original line where cursor was defined. You can see that highlighted on the left and flashing. I can click here, and that's going to include that line, and you can see it's now part of the example. You can see CodeScoop is also now asking me if I want to include a for structure. So it's providing these intelligent advice as to other lines of code that I might want to include in this example. In this case, it recommends all control structures that are between lines of code that I've already included. So this title equals cursor.getString is inside of this for structure. This cursor is outside of it. It recommends it. I can see this in context, realize that I don't really want this for structure. There's a couple of these others that I can review too. I don't really want this while structure and if structure, and it's going to be capable of preserving the behavior, and it adds noise to the example that I don't want. But one of the things that I personally think is semantically relevant to this example is including this try structure that wraps any calls to the database in catching a connection exception. I just think that's part of a clean database query. So I will accept this. And then it also recommends for this cursor variable other uses of this variable that might have modified it. So you can see, in this case, this cursor.execute query. This one and the fetch1 calls are both necessary for loading this data from a row into the cursor. So CodeScoop helps make sure that I don't forget any of this relevant code in the original program. I'm going to skip the rest. Another thing that we do with CodeScoop is, instead of just resolving code based on code from the original program, it enables people to make these simplifications to the code too, to hopefully make it more concise. So for any variable that we have dynamic execution data from the most recent execution of the program, we're capable of recommending these literal values that those variables took on during the program's execution. So for this column index title variable, I can set it to the value of 1, which was the value for this, essentially the index that this column took on during the program's most recent runtime that we got from instrumenting that program. And what this allows me to do is, if there were lines that ended up computing this variable through many involved steps, I now get to remove those completely. So I'll set that value there. I'll make a couple more fixes here, for instance, replacing this query with a literal value, the literal query that it took on during the program's execution. And then I'll also define this database by including the original variable too. And the last step is you saw that there were a bunch of automatic fixes that occurred, specifically those import statements that got added to the top. Whenever there's a choice, whenever there's a fix that could be made, and there's only one possible way of resolving it, CodeScoop makes that fix. And so in the case of these import statements, it's capable of inspecting the original program, identifying what import statements each of those types depend on, and just pulls them into the top of the file, resolving any of the ambiguities that might be there in a typical quick fix. Again, we have the original working program. Why don't we leverage some of the knowledge about how that program worked when helping people fill out a code example? So to summarize the scooping process, this all begins with initial selections of a pattern that a programmer wants to share, and then a series of resolutions and code fixes to that code example, pulling in other relevant code that will preserve the behavior that someone wants. Then a programmer can review other optional things to include, things like other uses of a variable or certain control structures that might add bloat instead of being important to the pattern that someone wants to demonstrate. You can choose to include those or not. And then there's also the step of including simplifications to the code itself, trying to eliminate irrelevant logic by replacing it with code simplifications. In this case, something like variable substitutions. And while these are the steps that are in the current version of the CodeScoop prototype, we see this as being kind of the first set of the family of primitives in the scooping and example extraction process. You can imagine other types of simplifications, things like substituting equivalent method sequences that are conceptually simpler to follow, or stubbing out these big objects with these more concise test stubs that are capable of replicating behavior if they're not really part of the behavior that someone wants to share in an example. So altogether, these selections, fix-ups, optional reviews, and simplifications are kind of the primitives out of which a scooping tool is built. In order to build a scooping tool, you need a bunch of different components. So you need to support a programmer after they have selected code in adding in forgotten lines, in being able to simplify the code, and also making some of these automated fixes. So some of the things that we orchestrate together in the back end of this tool is static data flow analysis in order to find all of the definitions and uses of a variable, to be able to locate the places where variables are defined. In order to help people simplify the code, we instrument the code at runtime in order to find out the values that objects and variables take on during the program's execution and being able to serve those up as options to simplifying a piece of code. In order to make automated fixes, for instance, like including these imports, we use reflections to be able to find out what import statements define certain types. And throughout all of this, we use a whole bunch of parse tree walkers, because what we have to do is we have to map locations from the analyses back to concrete locations in the original code that we can highlight and make interactive as someone is building up this example, mapping all of these analyses into these hooks in the code interface. So all of these things composed together make up a scooping tool. We ran a lab study where we invited participants to make examples with both CodeScoop and a baseline text editor. And what we ended up finding out was that CodeScoop was capable of removing some of that tedium and time-consuming nature of constructing examples that we saw in that formative study. Participants were faster when they created usage examples with CodeScoop than a baseline. They also reported that they found it easier to use, more enjoyable to use, and they were also happier with the examples that they created. But one of the things that I was most excited about seeing in this study was that there were actually many styles for extracting a snippet. We could give multiple participants the same task of a piece of code that they should extract an example out of, and they might resolve it in different ways because they had different conceptions about what a good example looked like. So for instance, when we asked some participants to do this task of extracting an example that queried a database for a row of data, one of the participants found it very important to wrap this call in a try-catch block, and also a check to make sure that the cursor had returned any data at all before getting data from a particular column. But another participant thought that it wasn't important to include any of this error handling logic, but they did want to give explicit variable names to each of the variables instead of literal values. And they also wanted to wrap up the saved data into this book data structure to show someone a little bit about what you might do with the data that you've queried. One of the cool things about this is that this really adheres to this vision of Bionic documentation tools, where automation alone can do a lot, but you still want to incorporate human insight into the process, because humans are capable of empathizing with and thinking about their audience and making these decisions about what they want to include in documentation and what they should leave out, and what's semantically important to people understanding how to do a task. So as a Bionic documentation tool, CodeScoop addresses the space of helping people generate these usage examples, encoding some of the goals that they have in those initial selections that they make in the code, encoding some of their empathy by allowing them to resolve these choices in multiple ways to help them build out an example that will be more suited to the audience that they're addressing, while also ensuring the correctness and completeness of the examples that they create. So that's the first Bionic documentation tool. And once documentation has examples, the next thing that it's going to need is explanations, written descriptions of what the code does, and how you can modify it in order to make it suit your purposes. That's what this tutorons project was all about. The case that we wanted to support with tutorons was, so say I'm looking for a command that allows me to download a bunch of data archives from an existing website. I might end up on a tutorial like the one that you see here, looking at a command like the one that you see right here, wget-r-l1-h, and a whole bunch of other options. And this is pretty close to what I need. If I change the value of that -a parameter, then I can make it download a data archive of a certain type. But as it turns out, this is broken for me because I wanted to recurse into the folders on this website, go several layers deep in order to find these pieces of data instead of just one level deep. And just looking at this, it's not really clear what I have to change. And if I rely on conventional documentation, for instance, these man pages that I might be able to Google, well, these things go on and on and on. In the case of this man page, it's 89 pages if you print it out on a laser printer. It's just really long. And while you can control F within it, it's still, a lot of this information is fragmented in different places. Sometimes it's an effort of just finding the authoritative place where this documentation is in the first place. And so for someone who's never looked at a wget command before, this can produce some barriers to being able to follow and modify these snippets of code. So what we envisioned was, we wanted to, for code snippets, some of these cryptic domain-specific languages like this command, or later I'll show you CSS selectors and regular expressions, we wanted to be able to detect these automatically, and then when someone found a code snippet like this in a piece of documentation, generate these context-relevant explanations on the fly, like the one that you see here. We wanted to do this in the browser, and in fact, we implemented this as both a library that people could incorporate into tutorial pages, as well as an add-on for I think the Mozilla browser, actually, because programmers do a lot of their information seeking and search in the browser. And what this project was all about was thinking about what these explanations might look like. If you could give someone a context-relevant explanation that explained just what someone needs to know in order to understand why a piece of code exists, what it does, and how to modify it, what would you show in it? This is one explanation that's built by a tutoron for the wget command line. And you can see that there are a few things that we thought was important to include in this. First, introducing the language, saying that this is a wget command. It's a command. It's a terminal command that lets you download pages from the internet. So for someone who's not knowledgeable about the Unix space at all, this is enough for them to get some context about what that code does. Then we give these high-level descriptions of what it does. For instance, it recursively scrapes web pages of type MP3 from URLs from the file mp3 sites.txt. And then the next thing it does is it provides this low-level breakdown of the syntax, but just the pieces of syntax that are in this command. So wget has around 150 options, and this shows the relevant help strings for just the 10 that were used in this command. This -r, this -l that the programmer is going to have to change if they want this to recurse deeper into the site, and so on. This project was all about thinking about if you could make these explanations automatically, what would you explain and how would you generate these explanations? You might want to explain individual tokens or full statements. You might want to explain what a language is typically for, or provide these links to other relevant references that someone might not have found on their own. How can we generate these? We can make string templates that describe common usage of these commands and these CSS selectors and regular expressions. We can use these rule-based approaches to build up these natural language sentences from scratch. We can leverage community tools because a lot of the time communities have already made these tools for understanding these hard to understand languages. We can take snippets out of existing documentation. We can render this ultimately as text, input-output examples, and diagrams. So what do some of these tutorons look like in the wild? So here is a tutorial page. And this tutorial page is, it's about web scraping with Python. And this web tutorial uses CSS selectors in order to identify elements in web pages out of which you'd want to extract data. And you can see highlighted in purple, here's a couple of CSS selectors that a tutoron has identified. This div pound video box h3, div pound sidebar a href caret equals / speaker, and so on and so forth. These are things that if you have never used CSS selectors before, or even if you're a little rusty on CSS selectors, if you want to be able to understand what these are doing and be able to modify these, it can be really challenging to understand how to do so without having like a really firm basis in CSS selectors. This is the type of explanation that are produced for this CSS selector tutoron. And you can see, like with the wget selector, we explain what selectors are for. We say, if you haven't seen them before, these are what selectors do. We also generate these natural language descriptions. So as it turns out for CSS selectors, the correspondence between a natural language constituency tree and a parse tree are actually pretty clear. You can describe how some inner element is getting selected from an outer element to be able to produce explanations like this selector chooses all links with an address that starts with speaker from div elements that have ID sidebar. And for someone who hasn't ever seen a CSS selector before, they can already start to do some pattern matching to know how they should modify the CSS selector. For instance, if they want to change something related to an ID, they now know that it corresponds to a hash mark. We also generate these input-output examples, again, starting at the leaf nodes of this parse tree, building up these pieces of an HTML web page that it would match, and slowly climbing that parse tree and generating these outer elements, showing that, for instance, this bolded anchor right here is what will get selected from a part of an HTML page that has a div with an ID sidebar and an ancestor with an anchor with an href that starts with speaker. You can also see that this tutorial has multiple tutorons enabled for it. So we have one for both these CSS selectors, as well as for Python built-ins. So it has detected this int one. And what we've done is we've snipped up the Python reference documentation, and we serve up the relevant doc strings from this, as well as pointers to the original Python documentation. We also experimented with incorporating existing community tools and visualizations. So here's a regular expression that appeared in a Stack Overflow post about server configuration. And you can see this diagram with the dark gray and the lime green. And what this is a railroad diagram. And you can read it from left to right in order to understand what this regular expression is doing. Matches a start of line, followed by an optional www, followed by any character, followed by domain, and so on and so forth. This describes at a fine-grained level what this regular expression is doing, and if you follow it left to right, you can get a pretty good intuition for how it's doing the match. The other cool thing is that with this particular explanation, you can find a bug with this example, which is that that dot should be escaped because it's actually matching any character, and since you're since you're trying to match a URL, it should really be \dot. We also generate these input-output examples. That's at the very bottom, where you can see that this pattern matches strings including wwp domain equals com and domain pipe com. This railroad diagram was actually generated through a tool called regexpert that already exists, that developers have created for other developers as an online web app where you can plug in arbitrary regular expressions to produce these visualizations. So a lot of this machinery is already sitting around. Why don't we plug them into these context-relevant explanations that can appear right in the places where programmers are asking these questions? So that's a little bit about how we explored this space of what to explain and how with tutorons for wget commands, for CSS selectors, regular expressions, and Python built-ins. There's a lot of boilerplate that goes into building these. So for instance, fetching these web pages and then traversing them in order to try to find these explainable regions, highlighting them, enabling these tooltips to appear on click, and having this communication between the web page and the server. We've abstracted all of this out into two projects, one of them on the server side and one of them on the library side. And so in order to create a new tutoron that is very basic, something that's capable of looking for particular tokens and serving up explanations from a dictionary, this is something that can be implemented with around 10 lines of novel code. If you want to do something more involved, that might require hundreds or so, but a lot of that boilerplate of detecting regions within a web page and then mapping them back to these explanations that you can display has already been done up front. So if anyone was interested in trying out this interaction, we've done a lot of that legwork for you. In order to better understand the potential of having these small context-relevant explanations as a tool for programmers to understand documentation, we did a pilot usability study where we gave programmers tasks like, for instance, writing a CSS selector that selects only elements of a specific class. And then we showed them a code example that was somewhat relevant to this task, but didn't give them the exact answer. For half of the tasks, we allowed them to access tutoron-generated micro-explanations that were capable of giving more context about what the snippet did. And we observed how often they had to access external documentation when performing this code modification task. Participants in general accessed external documentation significantly less frequently when these explanations were available, which is good. It suggests that these explanations are doing just what we wanted them to do, providing people with just as much information as they would need to understand and modify the code without requiring them to get bogged down in the details of external documentation. The Tutorons project represents another paradigm for Bionic documentation tools. Instead of helping programmers produce examples, it helps them generate these explanations. Unlike the CodeScoop tool, where a programmer and a tool worked hand in hand in real time, with the Tutorons project, a programmer invests a lot of their domain knowledge up front, building some of these detectors and explainers. But then after that, some of these explanations of code are capable of achieving much better reach than they would have had before. A programmer would have had to write these individually and figure out what were the relevant arguments, relevant parts of the syntax to explain in every tutorial. In this case, having a tutoron that's embedded in a web page or in a browser extension makes it possible to have these explanations anywhere that the code appears in context-relevant form. And of course, these explanations are also adapted to the code that someone is seeing. So I'll wrap up with our last project, which is a telemetry project that I did as an intern at Google last summer. We were interested in better understanding the types of questions that people had about C++ APIs. So let's say you're the maintainer for an API like this one, the abseil format time API. When people use an API like this, they're going to have questions about how to use it. Questions like, what is this second argument, this landing argument? What are the types that it can take? What are valid values to pass in? Questions like, will this crash if I pass in a past time rather than a current or a future time? And is there one of these % special characters that I can use to format the time for seconds or milliseconds? These are just three of a whole bunch of questions that people are going to have when they're coming to this API. And yet what we found was that when we're connecting with API maintainers as well as technical writers at Google, they all had these questions about what are the questions that the users are asking about these APIs? Is my documentation answering everybody's questions? The issue with answering this and finding out what questions people are asking about your tools is that typical typical techniques for finding usability bugs and software bugs just aren't really adequate for finding documentation bugs. Things like bug reports aren't likely to get submitted for documentation because a lot of the times they don't actually cause code to crash, or they aren't a blocker in someone's work. Surveys are inadequate because by the time that you send out the survey and get people's feedback, they might have forgotten about really important ephemeral questions for which they had already found the answers. Observation, bringing people into the lab and having them work, isn't so great either because these questions, the really critical ones with certain tools, might only come up once every few hours or so. So it's an inefficient process. We were working with some of the maintainers for C++ APIs at Google, and we came up with this idea about how we could connect with some of the questions that API users were having during their everyday work. Specifically, we had this hunch about C++ code navigation and how that related to questions. The idea was that in C++, code is divided between header files and implementation files. Header files include all of the method signatures for the functions, as well as this low-level usage documentation about how to call this function, what you pass into it, what you get back to it, the expected behavior of that function. The function itself is implemented in what's called a CC, or an implementation file. This is where the code that encodes the behavior actually exists. So all of the lines of code that implement format time are going to be in the CC file. And in C++, usually there is one CC file for every header file. Our hunch was that if programmers left these header files to open up implementation files, that might indicate that they have API questions, like those ones about what do these arguments do? Or will this crash if I pass in a parameter of a certain type? That might indicate that there's some questions that are being unanswered by the existing documentation. The cool thing was that at Google, like many other companies, they had this central code search interface for all of their code. Here it is right here. You can see there's this file browser on the left. There's this query bar up at top. And then you can look at the contents of the code in this main pane in the middle. Hundreds and thousands of programmers use this every day. And so what we thought is, if at that moment when someone leaves this header file to an implementation file, we could provide this short, easy to dismiss survey to ask about their questions, this would help us get to those ephemeral moments where people were having questions that weren't answered in the documentation. Wouldn't that be really cool if that allowed us to connect with programmers right at that moment? So we asked these questions like, which best describes the information you're looking for, and also to do a deeper drill down into the implications of this and the types of questions they were asking. What would be the most convenient location for you to find this information? And what question are you trying to answer about the API? We deployed this over the course of a couple of days across all of the C++ API code, and it allowed us to do some cool things. We collected a sample of API questions that people were asking as they were transitioning from header files to implementation files. For instance, what does the return value mean, and how can this method fail? And these fell into these 9 categories, which we labeled as these low-level usage questions about input values and return values about APIs, as these high-level usage questions about what are the recommended practices for using this API. What is the right API member and function to use if I'm trying to accomplish this task? And also these questions about implementation. So what are the hidden contracts about how I initialize this variable before I pass in, and who takes care of the memory with this variable? And these questions about implementation details and side effects, like, is this doing any logging that I should know about? What are some of the log messages that this emits? The other cool thing is that we got to ask about where the programmers preferred to find this information. And most of them, unsurprisingly, wanted to find this information in the header files. This isn't so surprising because they started out in the header files to begin with. This would have probably saved most of them time if it had been right there. But what's interesting to me is that even for some of these implementation questions, that light blue bar that you can see there, these were questions that participants, that our respondents also wanted to have answered in the header documentation. Something that is seen as inappropriate in like Java documentation specs, the fact that you would talk about any of that internal behavior that's outside of the contract and outside of what a method takes in and what it produces. And this really starts to blur the line between what belongs where, and if people think that these answers really belong in the header files, do they belong there even if our conventions say that we should mostly focus on low-level usage stuff in this header documentation? We also use this as an opportunity to connect with some of the maintainers for these projects that had questions that were going unanswered, in order to get more of an idea about why these questions were missing answers. And we found out what you might expect. One of the themes was that sometimes it's not the right time to document. So a team might be working on debugging the code or implementing new features and didn't really see it as the right stage to document right now. Other teams might have moved on to entirely other projects and really just wanted this project to die, even though people were still searching for it in the code base and finding it. This quote from the maintainer that I shared earlier, that it's unlikely that these files will ever get changed again. They would have forgotten this file existed. There's also this issue of this tension between keeping explanations minimal and concise and appropriately detailed. In the words of one of the maintainers, how often do you want to go into details which can easily be too much? If you answer every possible question about an API, you're going to have these walls of text that are going to get in the way of people navigating the code and reading any of the documentation. To me, this really underscores a few of the issues that these Bionic documentation tools are trying to address. In the case of it not being the right time to document, trying to reduce the amount of time that it takes for a programmer to invest so we can get the most insightful parts of them out while using the right machinery in the back end to guarantee this correctness and amplify the reach of examples and explanations. But on this issue of keeping explanations minimal and this tension between conciseness and detail in documentation, well, it's also something that we're trying to address with tutorons by producing these context-relevant explanations that can be viewed only when someone needs additional detail about this, and then it has these degrading levels of detail, from these high-level introductions of the language, these high-level descriptions of the behavior, all the way down to the fine-grained syntax of each individual token. As a Bionic documentation tool, this telemetry experiment was pretty unique, because its code analysis was very simple in comparison to the other projects. We were just looking at people transitioning from header files to implementation files. But it allowed us to do a couple of things that we couldn't do with the other projects. Use this tool as a way of helping programmers refine their goals and their sense of empathy and their awareness of audience as they were trying to put together their documentation. And to be able to amplify their reach by getting closer to people at the time that they were asking these questions, rather than having to rely on common knowledge or asking friends or relying on bug reports in order to find out about these documentation usability issues. Altogether, this is our third case in talking about these Bionic documentation tools. And another way that we can think about tools that leverage code analysis in order to help programmers capture, shape, amplify, and share programmers' insights with other people. And so while the highest level takeaway of this talk is that code analysis used at the right times can help capture and amplify programmer insights in new ways to make them more effective at documenting and remove some of these barriers. At a fine-grained level, from each of these projects, we also see examples of tools that provide different models of Bionic documentation. This idea of a tool that works hand-in-hand, real-time with a programmer and an editor that helps them simplify their code into something that will be tailored to a specific audience and share with other people a pattern that they might not have otherwise shared. The Tutorons project, which suggests this other model of Bionic documentation where all of this effort is front-loaded in this first encoding the knowledge step of figuring out how you convert found code into these explanations, and then allow an automated assistant to do all of the work afterwards in tailoring it to the individual code examples that are found and making sure to attach it to all of the places where it's relevant. And then this third example of these lightweight techniques that we can plug in at the right times, the right moments of code search and navigation in order to help elicit these questions that programmers have about their APIs and tools that are otherwise ephemeral and we wouldn't have been able to connect to without some form of automation. Altogether, this shows the rich space of Bionic documentation tools, the types of ways that you can integrate together code analysis and human insight in order to try to do these tasks of capturing, shaping, amplifying, and sharing programmer insight. And with that, I'd like to welcome questions. Sure. That's awesome.
So for tutorons, do you find that it highlights things that are not actually code, or like hashtags as CSS selectors and things like that?
Yes, so one part of this that I didn't mention in this talk was some of our work that went into trying to build out those detectors. There's a little bit of kind of handcrafted wisdom and trial and error that goes into trying to make sure that it detects the right things. With something like regular expressions, it can be kind of tricky because regular expressions appear in all kinds of different languages. So what you ideally want for height recognition is to find this in like Python, to find it in JavaScript, to find it in like TCL shell and like these weird config files for servers and that kind of thing. Whereas something like wget is something that the false positive rate is relatively low for, because you look for a code block that starts with wget, and then everything else is just that code example. So the answer is that mileage varies, and there's a little bit of handcrafted human wisdom that also goes into the process of trying to make sure that it's finding the right pieces of code.
And then second question is, have you looked into integrating any of these sorts of tools into browser developer tools? Because like looking at the JavaScript that's running on a particular page and then getting an explanation of what's going on would be really, really handy.
Yeah, that would be so cool. So, one of the ways that programmers often learn about things is by looking at other people's code. And so one of the places where I could see this as being really useful is like inside of like Eclipse developer tools or like Mozilla's debugging and development tools. I think it's a totally appropriate place to deploy something like this.
Hey, Andrew, I love that. Thank you very much. One of the things I thought was really interesting as a sort of meta example in all three of your cases was this way in which you pulled out this notion of empathy as being a value of documentation, right? That idea that empathy is part of coding and writing documentation is something that on one hand feels very alien to the set of values that we assume are part of this, and on the other hand seems to, at least with me, seems to resonate a lot. Having spent my time reading man pages that seem to be vituperative at best. I saw a proposal recently which I really liked, which was, do you know what growth mindset is?
Yes.
Right, this is like a big thing in all, classrooms, basically, right? The idea is that you don't, it's not that you don't understand regular expressions, you don't understand regular expressions yet, right? That being said, I've spent 20 years still not yet understanding regular expressions. But yeah, I wanted to pull that out, that notion of empathy as a value that seems to go across these. Are there other ones that you think may be values that we want to look at across the board in terms of helping programmers do what they do?
I'm not sure. So you mean like other inherently human things
Sure.
that we can bring to the documentation process?
Well, or other values that seem to be surfaced that may, I don't want to a priori assume that these are, a set of, should we say, soft human values, right?
Uh-huh.
It could be that it turns out leaving lots of white space is really valuable, right? And that comes up,
Yeah, that's a good question. I think, so one of the things that I didn't spend very much time on in this talk, but has been a part of some of the other tools I've worked on, is this idea of kind of the filtering that comes with domain knowledge, about identifying the things that are kind of important to a craft, identifying the things that go beyond language design and syntactic primitives to the idea of like how you might want to use something. One of the other projects that I've worked on in my PhD is about in the computing education domain, where we use program synthesis to be able to identify certain problems in student code and be able to match that to teacher feedback that can say more than just like you have an error on line 1 to saying like you might be missing a base case, or like go back to your lecture notes from chapter 5. And in those cases, that kind of higher level domain understanding of I guess, why things are relevant to someone and kind of what principles they need to draw on from their experience. That's another thing that's a part of this space that we've been exploring and that I want to explore more. It's an interesting question. I think there are other things out there besides goals and empathy, and I'd love to hear from you if there's anything else that you think is fundamental to just human communication that we can bring into these tools too.
Are there other questions online or in any of the commons? If not, I've got like 2 more, but I don't want to monopolize. So I want to follow up on. I have a note, my first note from your talk, and then you just brought it back up. One of the things that's very exciting about being Mozilla is we actually have people who write programming languages here. And you and I were talking earlier about how so often programming languages are not used by people, and yet we seem to have a reasonably good track record of writing programming languages that are used by people, which is wonderful. What are the implications of design for programming languages to think about these issues? Particularly, I'm thinking about of exemplars, shareability. Are there best practices that you've seen? I mean, your examples here were from a relatively small set of programming languages. Are there examples that you have? Are there things, for example, that work better in Java than C because of some inherent property of the language? And are things that we could learn from when building Rust or WASM or whatever else language we're going to have, and then I'm going to be bitchy about it, and it's going to turn out to be a massive success, right?
Absolutely, yeah. So there were definitely languages for which it was much easier to build these tools than others. So in the case of the CSS selectors, that was a case where we could traverse a parse tree in order to build up this natural language explanation. That's not something that we were capable of doing for wget or regular expressions, just because of the way that you would explain something like the way that parsed program would operate. So I think for the domain-specific languages case, there are certainly things that you can do in terms of the structure of the program as it gets parsed that can make it a lot easier to generate these explanations and enable new types of explanations. Anything that you can derive statically from code, in the case of wget, by just looking at the options instead of having to run it and understand what it does, if you can get meaning statically from code, that'll make it easier to generate these types of explanations. The other thing is that for a tool like CodeScoop, it's easier to build something that can make these correctness guarantees as people are pulling out the examples with a statically typed language that gets compiled than with a dynamically typed language that you don't know if there are bugs in it in some odd places. It enables you to reason a lot more about what the code is actually doing, make sure you're not leaving anything out. So I think if you want to make a scoopable language, static typing is pretty helpful. And if you want to make an easily explainable language with lots of opportunities to explain it, having these parse structures that correspond to ways that you might explain it, and having a lot of facts that you can derive from the static representation helps out an awful lot. I think it would be totally awesome if people kept this in mind as they were generating programming languages in terms of what might future documentation tools be able to do with what it learns from the language.
Well, and I like those as examples because they both seem to be correlated with human readability and human understandability. And rather than them being sort of specific tool-specific things, these are characteristics that I would suggest would tend towards more readable and thus less buggy languages, which seems like success all around.
Yeah, absolutely. It might be able to lend readability to the language itself, as well as the potential to use some of these tools.
Cool. Any other questions? We have a few more minutes. Anything Portland, San Francisco, Toronto, Vancouver, Alberta? All right. I'd like you to all join me in thanking Andrew very much for coming.